Thank you, Bill, and good afternoon. Our distinguished speaker today, Professor Lars Peter Hansen, is an internationally known leader in economic dynamics who works at the boundary of economics and statistics and whose research cuts across multiple disciplines, just like in this department. Normally, in introductions of this type, this introducer does not go all the way back to the birth of the speaker. But in this case, I will, and I cannot resist the temptation because Lars was born here in Urbana. And he spent his childhood years in Champaign, so he tasted both towns, the twin towns. But then he moved from this area and went to college in Utah State University, where he studied math and political science, and then to the University of Minnesota, where he got his doctorate in economics. Shortly thereafter, in 1981, he joined the Department of Economics at the University of Chicago, where he has been since then. Currently is the David Rockefeller Distinguished Service Professor of Economics, Statistics and the College, and also as director of the Becker-Friedman Institute for Research in Economics. Throughout these years, he has made fundamental contributions to many branches of economics, including financial economics and robust economics, that is, how to make effective decisions in the face of model misspecification. And he has received many prestigious awards, and I don't have time to list them all here, but they culminated in the 2013 Sveriges Riksbank Prize in Economic Sciences in memory of Alfred Nobel, more commonly known as the Nobel Prize in Economics. And this was for his early research on statistical methods to explore the interconnections between macroeconomic indicators and assets in financial markets. Lars Hansen's recent work focuses on uncertainty and its relationship to long-run risks in the macroeconomy. He explores how models that incorporate ambiguities, beliefs, and skepticism, which is very much related to today's talk, the skepticism of consumers and investors can explain economic and financial data and reveal the long-term consequences of policy options. Together with Tom Sargent, who is another Nobel laureate, and a number of other co-authors, they have recently developed methods for modeling economic decision-making in environments in which uncertainty is hard to quantify. They explore the consequences for models with financial markets and characterize environments in which the beliefs of economic actors are fragile. And this brings us to today's talk, which is titled Robustness, Ambiguity, Aversion, and the Price of Uncertainty. Please join me in extending a warm welcome to Professor Hansen.
So thank you very much for those kind words. I'm very pleased to be invited here. It's good that I'm very honored to be on the radar screen of areas of research that I've been influenced by extensively, although I'm not an official participant in. So today, I will talk about topics that are really important to the line of research that fascinates me right now, and namely the analysis of both how economic analysts and people that populate their models, the consumers, the enterprises, make decisions in the presence of uncertainty. As you'll see from my talk, my research has been aided by my interest in statistics, finance, along with economics. But also, I will draw important. I've drawn important insights from control theory, which has been rather fundamental in some of the research ideas I'll be talking about. While uncertainty is unavoidable and pervasive in our lives, in many discussions of economic analysis and policy, it unfortunately takes a back seat. I will discuss ways and reasons that we should instead push uncertainty to the forefront of our thinking. So as an economist, I build models. Why? I guess math is fun, but for some other reasons too. To represent clearly our understanding of the economy, to predict what happens when an economic environment is altered, such as changes in government policies, tax policies, exchange rate policies, monetary policies, and the like. The models that fascinate me are ones that are ambitious enough to confront macroeconomic questions, rich enough to feature a role for financial markets. Uncertainty is central to the models and how they are used. As in stochastic versions of control theory, the models are dynamic. They capture the evolution over time of economic variables. They include random impulses or shocks that are transmitted through the economy over time. This randomness is only one aspect of uncertainty, however. Another source is that some attributes of these models must be revealed through the use of data. As part of evidence-based scientific disciplines, such as economics, it's critical to have the willingness to measure and acknowledge the uncertainty to our answers to important questions. Finally, the models we have are not exact replications of reality. They're wrong. They're simplifications, and they're hence not perfect. Rather than dismiss imperfect models, I prefer to use them in sensible ways. The nature of these imperfections contributes to uncertainty broadly conceived. Here in particular, I exploit and adapt tools from robust control theory. So, given my experience as an economist, I'm convinced of the importance of uncertainty as a central ingredient in building and assessing models based on empirical evidence, and convinced of the role of uncertainty in influencing economic decision making. As I'll explain, there's several dimensions to this discussion that are pertinent to how economists build and use their models. The models that I work on incorporate investor anxiety and reluctance to go forward with new ventures in very uncertain times. Moreover, they provide, I would argue, a more sober framework for assessing economic policies. So in my presentation today, I want to explore a broad uncertainty from a very broad perspective. And I want to argue that this broader perspective is critical for economic analyses. While I don't expect you to become expert economists in one lesson, I hope you can leave this talk with a different perspective on the importance of uncertainty, at least in my discipline. So let me get down to business here. I'm going to do some art. This is some pieces spliced together here, and perhaps in ways that might look peculiar. The first real person that I know of that really wanted to use probability theory to confront social scientific data was Jacob Bernoulli. Over 300 years ago, he came up with the so-called law of large numbers, although he did much more than that, kind of characterize how from social scientific data with various replications, we can figure stuff out, like probabilities of things, like probabilities of urns, balls and urns when you don't know the fractions. If we look at the history of probability theory prior to Jacob Bernoulli, it was really about games of chance, situations in which we know probabilities, and then doing some more complicated calculations with those probabilities. Jacob Bernoulli pushed us into saying, well, when you look at social scientific data, we don't know probabilities. We have to use the data to figure it out, and he came up with this very elegant law of large numbers. So that's on one side of this figure, the left side. How about the right side? So think of Jacob Bernoulli like the statistician looking at economic data and models. What's going on the right-hand side is this painting by Pizarro. What's that painting of? It's a painting of a marketplace. When people come to market, they don't know how much demand there's going to be for their goods. They don't know what price might clear the market. They don't know how, but they have to make guesses. They also face uncertainty. They may not know probabilities of everything, but they can draw on experience to figure stuff out. I want to think about this picture here as two different perspectives of uncertainty. I think of the Bernoulli part as that uncertainty outside a model, the type of a statistician usually confronts. I want to think about the right-hand side of this, that of represented by the Pizarro painting as uncertainty inside a model. Economists are different than physicists. You know, my colleague John Cochran gave me some flattering discussion of me after he heard my Nobel Prize speech, but he missed one of the key points. He said, Hansen is like a physicist, wants to think like a physicist in terms of using formal mathematical models. And well, actually, economists are not like physicists because we've got to model these people, and they're a little bit different than the agents in models of physical systems. I'm sure that I'm abusing John Cochran's reference to me, but anyway, it's this how we confront inside the model uncertainty, though, is really a central part of model building in economics. So this is the contrast I was trying to make. Outside a model, so when I'm given a dynamic economic model, a researcher, a econometrician, is going to go and estimate parameters. It's going to assess model implications. But the model itself that we build, the researchers have to do things like depict economic actors, consumers, enterprises, and they cope with uncertainty. And then deduce the consequences for market outcomes and resource allocations. As economists, we have to think about uncertainty from both of these perspectives, the outside the model statistician perspective and the inside the model, investors inside the model making decisions. The interplay between these can also is something that fascinates me. So here's an outside the model uncertainty challenge that was posed by Frank Knight. This is why econometrics is hard, I guess, the field that I'm in. We must infer what the future situation would be without our interference and what changes will be wrought by our actions. We want to build an econometric model to help us think about policy. Fortunately, or unfortunately, none of these processes is infallible or indeed ever accurate or complete. Okay, so I'm going to come back to this, but this is Knight showing the challenges, the outside the model uncertainty challenges. There's a little bit of a bias here since Frank Knight was at the University of Chicago. I was reminded today that his son was at the University of Illinois for many decades in the math department, I guess, so there's a connection here as well, I suppose. I don't know if the son looked like the father, but anyway. No. So let me start talking. I'm going to start now moving to this uncertainty inside the model. We'll come back to the other topics subsequently. So economic model builders early on, building models of dynamic economic systems, had to cope with the challenge of expectations. Investors, when a person makes an investment decision, how much do I invest in my education? How much do I invest in some new capital project? You have to make guesses about the future. Just like these people in Pizarro's market have to make guesses about how much goods to bring to bear. And so it was necessary to kind of take stands on these beliefs. And there's this very powerful and demonstrably influential approach called rational expectations. It was kind of initiated by, in some sense, by Muth, but developed in all of its richness by my colleague Bob Lucas. And the notion here, the heuristic notion, is that economic actors or investors have long histories of data, and from that long histories of data, they can figure things out, including parameters. They know probabilities. They don't know outcomes, they know probabilities. It's just like the games of chance in the sense that the probabilities are given to them. This had some very important consequences. One is a model builder didn't have to think about how do we model people's beliefs, because once you write down the rest of the model, the beliefs are determined. Yield a so-called stochastic notion of equilibrium in which the expectations are now fully determined inside the model. It had a second very important consequence to it. It gave a coherent approach to policy analysis. Okay? Now, what I mean by this is if you kind of make up people's beliefs kind of arbitrarily or in ad hoc ways, and you start doing policy analysis, start shifting stuff around, you change the tax policy, you change monetary policy to a different rule. Do you want to hold people's beliefs the same? If you do that, then you run the risk of doing economic policy development, systematically fooling people. And to me that sounds like a very unreliable policy lever. And what rational expectations did is it pulled that off the table. You want to design policies that work without kind of imagining that over time you're going to just continually fool people. And so that, I think, is one of its most important and enduring contributions. And anyway, this was a breakthrough that's had just a huge impact on economic analysis in very productive ways. It's been very influential. But for my purposes in today's talk, and I spent the first couple of decades of my professional career pushing this very, very hard, it neglects some components of uncertainty by focusing on what I'm going to call risk. That is, economic agents they know probabilities of things. They've got that figured out. They just don't know outcomes. So I, as an econometrician, I would presume these people had this stuff figured out, and I, as an econometrician, would figure out this is very difficult. This is really hard. The models I write down are probably not right. I don't know which is the correct one. I'm struggling assessing them. Maybe there's a danger in pushing this a little bit too far, and maybe we need to also look at the consequences of pushing away from it. So I'm going to turn you. I've also had done work in the field of finance. So I'm going to turn you to an expert in finance in a couple slides. Anyway, there's not that much to it. So I should advertise. I've never in my entire career taken a course in finance. So maybe that will show. I don't know. So let me just give kind of a very simplified crash course in things. And so think about there being some type of stochastic cash flow that's growing over time. This could be some macro variable like consumption or investment, or just could be some cash flow on some investment project. Call that process G. Okay? It's going to grow, but it's going to grow stochastically between 0 and t. So I want to assign a value to a payoff G sub t. So I think a G sub t is a payoff on some project that's going to be evolving over time. I want to assign a price to that. So we have to discount it, okay? But it's uncertain. So you don't want to discount it with one number. You want to take into account the uncertainty. The different types of uncertainty say you want to discount it in different ways. So a convenient mathematical way of capturing that is a so-called stochastic discount factor, which has been demonstrably useful in a variety of empirical work. So I'm going to introduce this process. I'm going to think of this process G as potentially growing over time. I'm going to have this other process that's discounting the future, and it's going to, on average, decay over time, but it's stochastic because it needs to make adjustments for uncertainty. Asset pricing in its simplest form shows up in this formula for pi. What you do is you take the cash flow payoff at date t, gt, you discount it by st, between 0 and t, compute expectations, average over the different states that can be realized, and that's your assignment of price. And these type of representations and generalizations of them are kind of pervasive in the field of financial economics. So the stochastic discounting, what does it reflect? It reflects investor preferences, their so-called intertemporal margin rates of substitution for people who participate in the markets and the like. Lots of economics gets thrown into the specification of these stochastic discount factors. How risk-averse people are, how concerned they are about how much they care about the future relative to the present, a variety of entities, considerations show up in there, but also the actual nature of financial markets and who participates in them is also relevant for this. So anyway, that formula is going to be handy, and I'm going to come back to it a little bit. So roughly speaking, there's a process GT that's growing, and there's a process ST growing stochastically, and there's a process ST that we're introducing in order to determine prices that might clear competitive markets. Now, I'm going to go and use something called recursive valuation, and this is a very interesting history to it, and I'm going to draw some connections to what shows up in control theory as well subsequently here. Recursive utility goes back to Charlie Koopman's important work on the subject, and it was the versions of this that I'm being referring to is attributed to Krebs and Porteous, and was brought into asset pricing and macroeconomics in a big way by Epstein and Zinn and others. And this is a way to highlight how uncertainty about the future affects asset valuations through the preferences of the investors. It allows me to explore ways in which expectations and uncertainty about the future growth rates affect the valuation of risky claims to consumption. So it's going to allow me to investigate how beliefs about the future are reflected in current period assessments through so-called continuation values. And I'll elaborate on this in just a minute. And what this is going to do is asset prices are forward-looking. Asset valuation is necessarily forward-looking. And this gives us kind of a very convenient mathematical and commonly used type of specification for kind of how that operates. And we're going to see what role of perceptions about the future matter in these calculations. So here's a little bit of math. I'm not going to hit you with a lot of math because most people here are better at it than I am. But anyway, this is how the recursive utility works. This goes back to Koopmans, but modified or specialized in the sense of Krebs and Porteous. VT. I'm going to just call it. So economists like to use utility functions, okay? And so associated with I guess in engineering, we often use like discounted costs and the like. Well, we're going to have people maximizing expected utility here, and so this utility function is going to be specified recursively as followed. I'm going to call VT a continuation value. It's going to be determined by a bunch of future stuff. I'm going to have a consumption and a whole bunch of future dates. I'm going to collapse all that valuation into VT, but I'm going to construct it recursively here. Okay, so what I'm going to do is think of epsilon as some period of time. Think of VT plus epsilon as a continuation value from time t plus epsilon forward. Okay? I'm going to do a risk adjustment of that continuation value. So this RT is a way that I'm going to take that continuation value, raise it to a power, 1 minus gamma, and then undo it outside of it, a so-called certainty equivalent that economists like to use. So all this is going to do, the gammas here are going to be numbers that are bigger than 0 and typically much bigger than 0. And gamma is what economists think of as identifying risk aversion. Okay? So there's this risk aversion. I do this risk adjustment of continuation values. That's what this RT is. It's a way to make an adjustment for riskiness. There's this like discounted term, which I'm going to discount over interval epsilon. That's this exp of delta epsilon. And then I'm going to add on this term consumption. Now, both consumptions, that's current period consumption. That's raised to the power 1 minus rho. The rho is a parameter that economists think of as governing how people substitute intertemporally in their preferences. And the rho t here shows up in multiple places. So think of this as a recursion under which you start off in the future and then just keep on working back and getting to today. So you might start off at t plus 100 and then keep on working this recursion back and back until you get back to today. So it's this kind of backward look. It's this forward-looking recursion which you then solve backwards, just as in dynamic programming. Now, those of you who are familiar with so-called risk-sensitive control, completely independent of this was developments of risk-sensitive control going back to Jacobson, Whittle, and all, and it has a very similar flavor to it. There's this extra risk adjustment which is being made in the analysis, and this term RT can be connected back to recursive versions of say risk-sensitive control. The usual model used in economics was one in which you set gamma and rho to be the same parameter, and then what the Krebs-Porteous work or the Epstein-Zinn work did was allow us to have something that separately moves risk aversion from so-called intertemporal substitution. It gave us researchers ability to change preferences in multiple ways and to change risk preferences without affecting intertemporal substitution. Intertemporal substitution plays an important role in determining things like the term structure of interest rates and the like, and so it's handy to have something else that's allowing us to move around risk aversion. So this type of specification has been used a lot inside finance. Right? Now, the motivation is a little bit different than what came out of the risk-sensitive literature out of control theory and engineering. I'd like to think about it as motivated by the following simple experiment. suppose that you just consider the following lottery. It's an intertemporal lottery. One possibility is that you flip a coin. If you get a heads, you get good consumption. If you get tails, you get not so good consumption. So one possibility is you flip that coin once for all future time periods. The other possibility is you flip it every period, independently. The models, the preference models used by lots of economists would have you be indifferent between those two different gambles. You would be completely neutral on which one you would prefer. Flip it once or flip it every period. If you think that you might have a preference for flipping it every period, then the way that the kind of macro finance literature pushed it was to make this gamma parameter very different than rho, and to kind of give this preference for this kind of intertemporal diversification. But at the very least, these type of preferences allow for this richness, for the intertemporal composition of risk to matter, and so that's been demonstrably. It's been used a lot in my in lots of practical applications in my field of research. So I'm going to do some. We need to get to this so-called stochastic discount factor. How do we get there? You compute a bunch of derivatives and apply the chain rule, pretty much. What you want to do is you want to take that recursion and you want to figure out how a person has substitutes intertemporally between period t and period, say, t plus epsilon. So we compute what economists call marginal rates of substitution. Right? And literally, because of that recursion, I just got to compute a bunch of derivatives. I learned very early on in my teaching career that you never differentiate in public because you'll get it wrong. So I strongly urge you to presume I got this correct. I've had students check it, but they're smarter than me, so it's correct. The thing I want to emphasize here is 3 channels by what so this is how I do the stochastic discounting between t and t plus epsilon, and then I just compound this up. I just continually multiply it up to do it over multiple periods. There's 3 channels here. There's the usual discount factor. So we discount the future channel. That's the first one, expa minus delta. There's the type of channel that showed up in a lot of the early macro models. Consumption in the future, consumption today, with this parameter that governs intertemporal substitution, minus rho. Then there's this third term. It involves continuation value divided by risk-adjusted continuation value, raised now to the power rho minus gamma. If rho is equal to gamma, that term's gone. If rho is distinct from gamma, continuation values show up. So now I'm looking at valuation between t and t plus epsilon, but the future is mattering here because it matters through the continuation value. So the continuation value is going to, and that's going to depend on all your guesses about what's going to happen to the future. It gives a structured way to enhance the impact on the perceptions about the future. As I say, the special case that had been used a lot in macroeconomics was you set rho and gamma the same, you close this down. But to really confront lots of asset pricing evidence, it's very handy to have this extra forward-looking channel here, and lots of research has done exactly this. There's a very special case of this that again gets linked back to risk-sensitive control. And when rho is equal to 1, you can just kind of verify that that this term, this forward-looking term, involves raising things to the 1 minus gamma power, and it has conditional expectation 1. It's positive. Whenever you see something that has conditional expectation 1 and it's positive, there's an equivalent interpretation that's called that in terms of distorted beliefs. It's going to turn out that this is going to eventually get us a link to so-called robust control theory. But but that's jumping ahead of the game. This is just an observation now. This term sometimes can capture things like so-called distorted beliefs equivalently. But I'm going to come back to that. Okay. So anyway, the feature of these preferences, the key message I want to get out of this is the fact that even though I'm looking at valuation between t and t plus epsilon, it depends on all the future stuff through continuation values. So I want to think. So what's asset pricing about? Well, asset pricing is about the following, roughly speaking. Think of some asset with a payoff. The payoff depends on, I don't know, some future shock, some macro variable, say, some macro shock. it's exposed to uncertainty. Okay, the asset path's exposed to uncertainty. We want to figure out what the compensations are for that exposure. How do we? Any investor which is exposed to macroeconomic uncertainty that can't be diversified away has to require compensation. That's the theory of modern finance, basically, asset pricing. The type of uncertainties that gets to, if you're an insurance agent and you've got lots of people going out there and you're insuring a big population, one can average across all the outcomes of, of who has accidents and who doesn't. That uncertainty can be diversified away. Macroeconomic shocks cannot be, and that's why the connection between macroeconomics and finance is so natural. So those are the ones in which investors in security markets require compensation. So asset pricing theory kind of figures out what those compensations are. So I'm going to lots of engineering and there's applications of so-called impulse response functions, and the same is true in lots of macroeconomics. An impulse response function says, well, I take a shock today, tomorrow, and it's going to have an impact on variables in the future. So for the macroeconomy, future investments will be shifted, future consumptions will all be shifted, and a lot of the way the implications of macro models are summarized as working out these so-called impulse responses. How do different shocks affect future values of the various different macro time series? And this has been a common kind of workhorse in empirical macroeconomics. Now, I want to take this one step further. When the shock, I want to think of the shock as changing the exposure to uncertainty. If it's changing the exposure to uncertainty, that has to be compensated. Investors exposed to that have to be compensated. If a shock tomorrow affects the macroeconomy, the next day, the day after that, then there's going to be pricing consequences over all those different investment horizons. So I'm going to start showing you the pricing counterparts to these impulse response functions that are kind of commonly used in both economics and engineering and kind of other disciplines. But I'm going to put a pricing counterpart to it. It's because whenever I'm looking at macro shocks, investors have to be compensated for it. And different models tell me how those compensations work. It's a kind of a dynamic notion of characterizing so-called risk prices. So formally, you can do this. The mathematical tools. Well, we start doing stochastic perturbations of existing stochastic systems using so-called Malév derivatives. These are just continuous time stochastic calculus. And they lead you to altering risk exposure by changing probability measures. So changing a risk exposure requires compensation. That's the risk-return trade-off. The mathematical tool that goes along with that is, well, we can think of that equivalently as a change of measure, and then mathematically that's convenient. It's a so-called Gersanov theorem. I'm not going to show you any more details of that. I kind of understand it, but I'm not going to talk about it. I'm going to have you trust me again. This is a little bit harder than algebra, but well, maybe but not much. Okay. So now I'm going to write down. I'm going to write down a demonstratively simple model here that's supposed to capture some features of the macroeconomy. Think of log CT as just a stand-in for how the macroeconomy is doing. Think of it as being aggregate consumption. The aggregate consumption here is going to evolve, okay? And it's going to evolve. There's going to be a state variable governing its conditional mean dynamics. That xt1 there. xt1 is going to evolve like a so-called first-order autoregression, except it's going to have this xt2 variable here. This xt2 variable is going to be so-called stochastic volatility. Economists are very clever at making stuff up, so we make up stochastic volatility to get things to move around in interesting ways. I'm going to come back to that. So the xt1 is it just died on me. There it goes. xt1 is capturing the predictability in the macroeconomy. xt2 is capturing its volatility. Both are going to be these persistent processes. There's going to be three shocks to this economy. I can make macro models a lot more complicated than this, but I'm going to keep it simple. There's one shock is going to have permanent consequences. One shock is going to have only transitory consequences. The third one is going to be an independent shock to stochastic volatility. Okay? Exposures to each of these shocks require compensation. Okay? Now what I want to do is I want to compare this, two models, the so-called recursive utility model to the one that was used more extensively in macroeconomics that I talked about before. And I'm going to give you some pictures. The recursive utility model, the gamma different than rho model, the model with a forward-looking channel, beliefs about the future matter. Now I'm going to have these so-called risk prices, these compensations for every different investment horizon. There's a shock tomorrow. It's going to affect consumption in all the future dates. How it affects it is going to be tracked very proportional to kind of what that red line is. Remember, there's kind of this persistence in the economy. So the permanent shock shifts consumption immediately, and then eventually shifts it more and more and more and more. Okay? The rho equal gamma economy without this forward-looking piece, the compensations just track the impulse responses proportionally, and that's kind of captured by this red line here. The recursive utility model with this forward-looking piece, where continuation values really matter and have to be computed, is the top flat line. Okay? The band here is capturing the so-called stochastic volatility. That the prices move around because of stochastic volatility. What it does is this permanent shock. The one model eventually gets big prices. The other model with the forward-looking channel gets compensations that are big immediately. And for asset pricing, to explaining asset pricing facts, that's really key. So the empirical success of this model, in part, is the fact that because of this forward-looking channel, you don't have to wait 40 quarters before you get the big effects on prices. They actually occur immediately. Now, for a temporary shock, it's basically just the opposite. The forward-looking channel says, who cares? The compensations in the blue line are trivial as a consequence. The red one is you just kind of trace through how the temporary shock eventually goes to zero. So it's non-trivial compensations immediately, but they just decay to zero by the temporary nature of it. There's a third shock here, and that's a shock to stochastic volatility. If you're an investor and you're exposed to a shock, to a change in the macro volatility, that also requires compensation. The model with a forward-looking channel is the compensations are big immediately and fairly flat. The other model is they start off at zero and they eventually build. You have to wait 60 quarters or more. And the model calculations I've done here that were lifted from some early papers in this literature, the important compensation then, the exposure to which macro shocks that get the biggest compensation implied by this model are these permanent shocks. The shocks of stochastic volatility get compensations, but they're not nearly as big as these. And so exposure to that shock is the one that just helps differentiate different security prices and their expected returns, according to this model. So this is a model that's been used a lot, and I want to kind of discuss it a little bit more as to the success here is we have this permanent shock that starts getting very big prices, not eventually, but immediately. How does the mechanism work? Let's go back to rational expectations. The way people solve the model is investors know all those parameters I wrote down there. The same models that I simulated with, investors just know it, and they're 100% confident in those parameters. Now, if I were a statistician who tried to estimate those parameters from primitive data, it would be the amount of information on some of those parameters would be very, very sparse. They're hard to estimate. So where does this confidence come from? How is it investors? So the success of the mechanism is if investors know it, it shows up at a big impact on asset prices. Therefore, they must know it. But since we know there should be a big impact on asset prices, but that starts becoming a little bit circular. But a lot of the literature is based on that type of confidence. Investors figure it out. Econometricians don't. There's another part of this is that stochastic volatility. I said we kind of just made that up here. Where does that come from? Yes, we do think that macroeconomies are more volatile some periods than other periods, but what drives that? We do think that we know well that financial markets are more volatile in some time periods than others. What drives that? Here it's completely exogenous. This This mechanism that I talked about imposes a risk aversion parameter that's large. That is, if you ask people gambles with known probabilities, it's going to look like people are incredibly risk averse. Perhaps there's something else driving it. It's not just risk aversion, and that's what I want to turn to as well. So I want to kind of push the success, the success illustrated by that figure I just gave you. I want to try to see if we can't get at some of these issues in a little bit different way than that story. So what I like about that story is the forward-looking stuff matters. But the investor confidence and the stochastic volatility, stochastic volatility is kind of just a mechanical solution to how we get volatility in financial markets, and it'd be nice to push beyond that. The large risk aversion should be troubling. So to go forward, what I want to do is draw a distinction between multiple components to uncertainty. Risk. If I write down a model, I know all the parameters, it's going to tell me probabilities of all the future stuff. So what probabilities does a model assign to events in the future? I'm going to call that risk, right? I'm going to introduce two other things. Model ambiguity. Suppose they don't know which is the right model. Suppose they don't know which is the correct parameter. How much confidence do I place in each model or in each possible parameter configuration? I'm going to distinguish that from risk, and I'm going to call that model ambiguity. Okay? There's a third component, model misspecification. That model I wrote down is pretty simple. It misses a lot of aspects of the macroeconomy almost on purpose. And if we look at the more micro details of the model, I know it has to be horrendous along some dimensions. Yet I still think it's a useful model. How do we use models in our decision making? They're not perfect. But the potential presence of model misspecification is another source of uncertainty. And this is where robustness considerations start coming into play. So in fact, it may be that the third one is the most important component to uncertainty. Most of the research that we do in economics focuses on the first. So the second one was this so-called ambiguity, which is the right model. There was a solution to that. It was proposed by Savage, who was at the University of Chicago, and he built on some very important insights from DeFinetti. And they developed a school of subjective probability. That is, in places where we don't know probabilities because we kind of, through introspection, through other sources, we come up with these subjective views of things. And Savage produces this elegant axiomatic system showing us that this is kind of, there's a sense in which rational decision making should proceed along these lines. So like when I talk to my colleagues, my theoretically inclined colleagues in economics, they always say, well, Savage solved the problem. He produced a set of axioms. We know how to proceed. Well, did he? So let's go back to the authorities themselves. These are the people who really produce the theoretical underpinnings for this so-called subjectivist approach. In DeFinetti, subjectivists should feel obliged to recognize that any opinion is only vaguely acceptable. So it is important not only to know the exact answer for an exactly specified initial problem, but what happens changing in a reasonable neighborhood of the assumed opinion. This to me says you have to do some form of sensitivity analysis and not pretend these subjective probabilities are just known. Savage, no matter how neat modern operational definitions of personal probability may look, it is usually possible to determine personal probabilities of events only very crudely. So even if we go back to the authorities of subjective probability, it seems to me like they're sympathetic towards pushing beyond just the subjective probabilities. Just allows us to think about things just like risk. Okay. So here's a commercial break, kind of. So let me just, Chicago, where I work, is a tough place. I'm going to give you two illustrations of it, and I'll come back to this picture. First is Savage did some of his most important work at the University of Chicago. He left for personal reasons. A year or so later, he wants to come back. His colleagues refused to take him back. I guess he was not the most pleasant person in the world, but in my department, I think that would be to your credit if you weren't so pleasant, so it would probably welcome you back. But the statistics department, which I also have an appointment in, is a little bit different culture. The other story is the following. Steven Stigler, who is in the statistics department and a good friend of mine, wrote a survey article on robustness in statistics, and he took a book cover that Tom Sargent and I had, a book called Robustness. Now, our book cover is most of this picture. This is why this is a commercial advertisement, except it left off this person right here, which I'll come to in just a few minutes. Those of you who know about robust statistics, one of the approaches to robust statistics is to lop off outliers. And Steven Stigler noted that Sargent and I had happened to lop off an outlier that was perhaps the whole key to the painting, and therefore it may be a dangerous practice. So he used our abuse of this beautiful painting by Latour as kind of a platform for a survey on robustness. That's why I say Chicago's a tough place. I asked Steve how collegial this was, and his response was quite simple. He says, "I'm sure that I helped your book sell more copies, and I look forward to the check you send to me for the additional copies that were sold as a consequence of his article." Stigler was right. This painting, the publisher made us lop off this part of the painting, so I'm not going to feel totally guilty about it. But let's now talk about this painting. As I said, this is a painting by Latour. In fact, there's two paintings by Latour that are very similar in distinct museums that I'll get back to as well. So here's a person playing cards, naively thinking this is a nice, simple game, more like a game of chance. There's some strategic elements in there, but probability calculations could be potentially very useful here. Unfortunately, there's this other person back here with some cards behind his back. Apparently, the dealer here with the shifty eyes maybe knows what's going on. Perhaps the person pouring the wine does as well. Not surprisingly, this painting is called The Cheat. What's this doing here? So if we want to use models naively, maybe we would proceed like this person, but maybe our models are wrong. Now, if they're wrong, maybe it's useful to think about, are they wrong in consequential ways, or are they wrong in inessential ways? And the whole notion of kind of robustness is in decision making is all looking at what type of mistakes are consequential and trying to figure those out. And in some sense, trying to move from a naive person like this to people doing systematic assessments of what happens when models aren't quite right. A perspective that I find quite useful. Enough for the commercial break. So how do we make robustness operational? So going back to the Di Finetti and Savage, in dynamics, so like Di Finetti and Savage, their subjective approach to probabilities gave rise to a richness of Bayesian statistics, and it's been a hugely influential field in a whole bunch of disciplines, including mine. I guess my perspective on this is that I think it's still very valuable to put in robustness considerations into this, because there's still subjective inputs, and sensitivity analyses are still relevant, as suggested by the quotes from Di Finetti and by Savage. Now, in dynamic context, so how does Bayes' rule work? Well, you start out with a prior, you get data, you update it, you get a posterior. In a dynamic context, yesterday's posteriors is today's prior, so it's kind of it's not quite clear what I want to call it, but anyway, it's a priors posteriors. These are how we weight models, but at the very least, in the Bayesian perspective, gives us a beautiful theory of dynamic learning, but it shouldn't close down the considerations about robustness. There are subjective inputs, and doing sensitivity analyses can remain very, very useful in those, especially as we're looking at models that are increasingly complex. Alternatively, we can think about kind of exploring alternative potential models or class of perturbations to a benchmark model. And these future perturbations may not be tied to past evidence, therefore making learning about them impossible. Changes in the model that might occur tomorrow or the next day might not be tied to historical information. Again, this notion of robustness, these type of concerns have both control theory and statistical origins. posing a decision problem allows us to target the member of these families that has the largest utility consequences. And so it gives a structure to doing these robustness type analyses. So what does modern decision theory and control theory tell us? So there's modern decision theory within economics is very axiomatic in nature. It produces these wonderful axiomatic foundations about saying, trying to get at what it means to make rational decision making in the presence of different notions of uncertainty. So it can often give rise to axiomatic foundations and tractable representations and so-called recursive constructions. Now, the thing that's very handy out of control theory is a control theorists are always giving us tools that are actually usable, tractable, and valuable for practice, which decision theorists in economics are not always is not always on their radar screen. Combining insights from both can be tremendously valuable. Now, what is missing here is a fully fleshed out theoretical justification for a sensible model construction of misspecified models. How do we build a model that's simplified? We think the environment's much more complicated. What are the exact rules for doing this in a sensible way? Once I introduce new concerns about uncertainty, not knowing what the right prior is, not knowing which among a class of models, I invariably introduce new parameters. What is the best source of these new parameters? And kind of clear discussions of it. In some of my work with Sargent, we've explored some aspects of this discussion, but it's very important going forward. Finally, I mentioned that Knight quote about policy analysis. How do we do, what parameters are we allowed to keep invariant as I change the environment? If I change some economic policy, maybe the policy itself is going to reduce the amount of uncertainty, or maybe it's going to have some impact on how people think about uncertainty. What's the right way to think about doing these counterfactual analyses that are important for a policy, for policies? So part of my title was ambiguity aversion. Well, ambiguity aversion is a term that's used by people coming out of economic decision theory. And then robustness is something which we've lifted from statistics and from control theory, and they have very, very similar aims attached to them. But anyway, I'm going to kind of go ahead with kind of what I think we can get out of this type of framework, but trying to think about these other components of uncertainty. So now I have to go back to asset pricing. To modify that formula I showed you before, I have to modify a little bit. So if I don't know what the true model is, and I'm doing some type of robustness analysis, I have to look across models, or I have to look at, and so that the way that the so-called decentralization of this works, that once I start looking across models, I do some type of worst case analysis, constrained, penalized, or whatever. The way you support the asset prices is off the solution to that. And so you end up having to use distorted expectations to represent asset prices. Well, where before the stochastic discount factors, we're now changing expectations. Okay? Now, we kind of know from probability theory that a very convenient thing to be doing to represent distorted beliefs or changes in probabilities are martingales. And so we can represent these distortions by martingales in very mathematically convenient ways. And so we can do that, and then it can return to the original so-called correct expectation, given by this E here, provided, so I go down to this bottom line here, provided that I change the stochastic discount factor to have two components. The stochastic discount factor under the distorted beliefs times this new channel. And the aim of a formula like this is, instead of making people making risk aversion do the bulk of the work in coming up with stochastic discount factors, now I can start thinking about belief distortions. And the fascinating part of this formulas like this is, could statistically small changes in beliefs, ones that statisticians would have a very hard time telling apart, give rise to important changes in valuations of asset prices? If the answer to that is yes, then this becomes a very potent channel to be exploring. And so maybe these high risk aversions, which are being recorded in some of the asset pricing literature, is really instead coming through this other channel. Concerns about the model not being quite correct, concerns about it being potentially misspecified and the like. Okay, so the formalization of this, in the work that I'm going to be doing is I might kind of I'll be building on some analytical convenience and tractability from robust control theory. uses constructs so-called conditional relative entropy. These ideas go back to Jacobson and Whittle. There's important work by Bassar, James, and others which we're able to build upon. We have to turn this into a specification of preferences. So we have to modify things a little bit. We have to show some type of recursive way to represent preferences. In some of our work, we propose how to do that. It's been axiomatized by some decision theorists, Mascheroni, Marinacci, and Rusticchini. Now, what this does is a relative entropy provides a rationality for so-called exponential tilting of these continuation values, which I talked about before. So by taking this approach, this so-called recursive utility model, instead of thinking about making this additional risk adjustment, this term here that I said had conditional expectation 1 now becomes an adjustment for model misspecification. So this relieves me of having to make risk aversion tell the whole story. Instead, it might be statistically small amounts of concerns about model misspecification might be imitating the impact of risk aversion. This is the kind of pricing counterpart to the links between risk-sensitive control and the robust control, familiar from the control theory literature. So this gets us part of the way, and we use this apparatus in some of our work. But there's still no endogenous source for fluctuations in these uncertainty prices. This just says that we can make things big, but it doesn't say why they're big sometimes rather than other times. And the evidence in financial markets is that's exactly what's going on. There's fluctuations that are important. So how can we push this further? So here, I want to do the following. There's two different approaches which we've proceeded in various places. One is structural misspecification. Take that model which I wrote down before. There's parameters like how much persistence there is in macroeconomic growth rates. How much persistence is there in stochastic volatility? Okay. Well, let me close down the stochastic volatility channel and just target on macro growth rates. Okay. So we're estimating the persistence in macroeconomic growth is a very challenging thing to be doing. And moreover, it may be fluctuating over time. The model that works today may not be the same one that works in the future. Putting in structural forms of misspecification, allowing for these, can provide a source of dynamics and fluctuations in these uncertainty prices. There's a different way that gets at this as well. Robust learning under misspecification, so-called the fragile belief channel. Suppose you don't know how much persistence there's going to be in the macro economy and growth. Okay? And think about good times versus bad times. In good times, persistence in macroeconomic growth is great. The good times will just continue. The models you fear are ones in which there's not much persistence because it means the good times will disappear soon. Flip it to bad times. If you're in bad times, persistence is bad because it means the bad times are just going to continue. The model you fear now is going to be the model with lots of persistence. Your perspective on a good and a bad model changes as the macroeconomy itself changes. This provides a new mechanism for how for some kind of fluctuations in asset markets. So like, through the financial crisis, say we don't know what the correct model of the macroeconomy is. We may have some doubts that gives forms of structural misspecification. Moreover, when we're learning, when we're going through good times and bad times, our perspective on what good and bad models are fluctuating as well endogenously. These are the type of mechanisms that I find fascinating, and by enriching this notion of uncertainty, we're able to put these on the table and to explore them systematically. So let's take this model here. This is like a simplified version of the model which I showed you before. Okay. And I've closed down stochastic volatility. I've got log consumption as be the proxy for the macroeconomy. I've got uncertainty about the growth rate in the macroeconomy. Suppose I want to allow for this persistence parameter kappa to be different in different time periods. Okay, as an approximation, I might take a constant, but I want to allow it to be shifting. Okay. I'm going to disguise these shifts inside Brownian motion So, they're small statistically. A statistician's not going to be able to figure them out very quickly. And if changes in the future aren't connected to the past, there's not going to be much of an ability to estimate things. There's little reliable information we have on mu and kappa. Okay. So what we want to do is introduce a concern about robustness. Maybe I don't really know what kappa is. There's a family of alternative parameter configurations I might want to entertain, and I also, at the same time, want to allow for other forms of misspecification as well. Now I'm starting to think about risk-return trade-offs. There's an interplay with not knowing what some of these key parameters are and kind of what effect it has on things. So I'm going to just repeat these uncertainty price calculations I did before for this model. So we're going to take this, we're going to imagine we're going to disguise these model misspecifications inside some Brownian increment. That's going to make it hard for a statistician to figure things out. And we're going to, in very convenient ways, like coming out of the control theory literature, we're going to start penalizing some of these distortions. Now, without this structured form of uncertainty, our earlier work, these distortions came out constant, and so there was no source of fluctuations. By allowing there to be these parameter shifts, then this gives a kind of state dependence to the nature of these distortions. And the worst case model happens to be inside the parametric class, which I wrote down, but solved out endogenously. So here's, so basically what we're doing is allowing for misspecifications by adding these drifts into Brownian motions. They could be dependent on the past in very general ways, but there's a class of these which we want to allow for. We want to allow for specific shifts in the parameters of the model and make sure that those are feasible among the ones which we consider. We want to consider other models that are also hard to distinguish via statistical methods. So this is just some mechanical details that go along with this. We're going to look at some convex family of martingales that are similarly hard to distinguish, and we're going to introduce a penalization parameter that helps us think about this. We're going to calibrate the penalization parameter to measures of statistical discrepancy between models. So now the outcome. Now we can get large uncertainty prices without large risk aversion. Moreover, uncertainty prices are larger in bad times and good times. So evidence from financial market data is that these risk-return trade-offs look bigger in bad times and good times. They look more severe. This can get it as a kind of endogenous mechanism of people struggling with the nature of the models on the table. So here's an example. So the calculations off of this, which I've just been very sketchy about, think about the original growth rate of the macroeconomy going along the trajectory of that black line. And then the model gives it a band around it because there's certain amounts of uncertainty, and that band's going to expand as they go out more and more horizons. What I'm going to do is I'm going to act as if I'm going to solve out this corresponding worst case model as a way to induce more cautious behavior on the part of investors. That's going to be investors don't take this model literally. They take this as a way to implement robustness. This is a model that's more conservative. The macroeconomy is going to grow at a more conservative rate, and then this is the associated band that goes with it. Okay? So even though the baseline model is this black line, the conservative adjustment leads me to also focus attention on this line here, and this is the calculation that drives the asset pricing. The gaps between these two things are kind of what's interesting. So the uncertainty prices, just of the type we talked about before. Suppose I got these shocks going on to the growth rate of the macroeconomy. That's going to be this red line. It's going to have this flat trajectory like we had with recursive utility because you're looking at the consequences for the misspecification for the entire discounted expected utility function. The future matters in these calculations. It's part of the endogenous calculations. That gives us these impacts immediately and big and fairly flat. The bands here are these interquartile ranges. The actual prices are going to be fluctuating within these bands in kind of persistent ways. And they're going to be bigger. These prices are going to be bigger in bad times and good times. But here we're getting this endogenously instead of exogenously. Okay, I'm probably over time, so I can stop now or I can make a few more comments. Okay. So I want to talk a little bit about policy. 5 minutes. Economic policy, why not? Anyway, okay. So Hayek, this is from his Nobel address. Hayek shares the Nobel Prize with Myrdal. He's probably not too happy about that. They're very, very different in terms of their perspectives on social science. Hayek writes this Nobel. When you get the Nobel Prize, you're supposed to write this address. You're supposed to explain why you got it, which is like nobody ever does because it's too boring. But Hayek kind of challenges to what extent economics is really a science. He just gets the Nobel Prize in economic sciences, and he's asking to what extent is economics really a science. It's kind of interesting. But there's a part of this that I think is really important. Even if true scientists should recognize the limits of their study of human behavior, as long as the public has expectations, there will be people who pretend or believe that they can do more to meet popular demand than is what is really in their power. This is this distortion we have that politicians, like economists, that have extreme confidence in their opinions. Now, economists with extreme confidence, then there'll be other economists with similar confidence that will disagree with them, and usually they're disagreeing because the evidence is weak. But to influence the policymakers, they have to project this great confidence, and that's a way to have public discourse, but it may not be the most productive way. And the Hayek concern here, I think, is a relevant one. Is that we really want to load up this discussion on people who pretend to or believe they can do more to meet popular demand than is what is really in their power. So some problems that face us today, like financial market oversight and uncertainty. Because of the financial crisis, there's a term that came into play called systemic risk. It was used a little bit prior to the financial crisis, but since then it kind of taken over lots of policy discussions. What is systemic risk? That's a wonderful question. There's a famous Supreme Court Justice, Potter Stewart, who's talking about pornography. You know it when you see it. He wasn't going to tell you what it was. There was a little bit of that flavor to this. And I think it should really be systemic uncertainty. It became a grab bag for doing financial market oversight. But key players like Trullo, who's on the Board of Governors, or Andy Haldane from the Bank of England, they say explicitly, you're asking us to use this construct, and the academic knowledge and understanding of it is very, very limited. So once we acknowledge our limits, so it seems to me a more prudent notion of policy making should acknowledge our limits to understanding linkages between the macroeconomy and financial markets. Each individual specific model, I could spell out the details of the macroeconomy with a whole rich set of financial market structures inside of it, and it may imply some type of complex solution. I remember going to many conferences where people in the Federal Reserve Bank would research departments that say, well, financial market oversight is a really complicated problem, therefore we should do so. It requires a complicated solution. If you really have a limited understanding, it may well be that that simple, robust policies may avoid adding uncertainty to the economic environment, may be the more prudent ones. So by putting uncertainty on the table as a serious consideration, we may well be led to different types of policy calculations. Now there are Charlie Evans, who's the president of the Bank of the Federal Reserve Bank of Chicago, is an old friend of mine as well. In one of his more sobering discussions, I thought of policy. I found this to be very useful. He's basically suggesting we take a more robustness approach to thinking about policy analysis. He says, I see two important and divergent ways my forecast could go wrong. Most Federal Reserve Banks presidents don't say this, but he did. One is I may be overestimating the underlying strength in the real economy. Guarding against this risk calls for more patient removal accommodation. The second is I may be wrong about the inflation outlook, and we may be poised for a much stronger rise in inflation than I'm forecasting. This risk calls for more aggressive rate hikes. So this notion that there are competing models on the table and they have different predictions for policy, and then prudent policy is going to have to trade off the consequences of these policies under the different divergent views. And I think that's a more intelligent and more prudent way to engage in the policy discussions. I could go on. I could talk about climate science and economics. That would, but let me not do that. Let me summarize. I'm trying to talk about these two perspectives on uncertainty. Outside a model, the statistician role, policymakers who use models, that's their perspective. Inside the model, when you build models, we've got investors. They have to make decisions. Those decisions, they have to cope with uncertainty. I like to distinguish the multiple components to uncertainty. risk, the model risk, that's the one which, at least in economics classes, we teach the most about. The models assign probabilities to the future. How do we cope with that form of uncertainty through risk aversion? Model ambiguity. How much confidence do we place in each of the potential models? Third, and perhaps most important, but most challenging, model misspecification. How do we use models that are not perfect? Now, what I find attractive to looking at uncertainty more generally is new sources of fluctuations may emerge in security market behavior. I also think it opens the door to a more sober perspective on economic policy. So I firmly believe in the virtues of thinking about uncertainty in these much broader terms. Thank you.
Well, even though we are a little bit over time, I think we do have time for questions. So, yes.
Illinois.